All right, guys, in this video, we're going to talk about quantifying energy conservation. And this is kind of a review lesson, so you should already be familiar with this as a concept. And I'm just going to kind of run back through it as a way to kind of review so that we can start moving forward. So in this video, I'm going to talk about energy bar charts just a little bit. We've already covered that pretty thoroughly, but we'll talk about it just a bit. And then we'll talk about how to quantify energy conservation by using those bar charts and kind of applying math to it, and then we'll do some examples. So the goal here is to demonstrate and apply the laws of conservation of energy in one dimension, and that is the level 3 standard. So we want to be able to look at conservation of energy and apply it to a specific situation, and use that to try and solve for an unknown value or make a prediction. It's really the predictive power that we're looking at here. So when we look at quantifying energy conservation, we're going to start with making energy bar charts. That's a super critical step in what we're doing here, is being able to start with a representation of the different types of energy that are present. And then what we want to work on doing is to quantify that, I've got to kind of translate that into math. And so the next step then is essentially its translation. We want to take the energy bar chart and we want to write down mathematical statements to represent that energy bar chart. And then step 3 is going to be where we equate the bar charts. So the idea here is that if energy is conserved, so this is a really acknowledging of the conservation. If energy is conserved, then I should be able to set any two of those mathematical expressions that I've created in the previous step equal to each other because they represent the same amount of energy. And then all I have to do is go ahead and solve for the needed quantity. So let's take a look at what this will look like here. So I've got a 3.5 kilogram ball that is dropped from a height of 2.3 meters, and I want to know what the velocity is when it reaches the ground. So it's a pretty standard basic question. So let's look at a little doodle of what this would look like. So I've got a ball that's going to try and drop some distance, and we've said that distance is 3.5 meters. And I also know the mass of the ball, so I'm just going to go ahead and put it up here that the mass is 3.5 kilograms. And so the first step here, if we kind of go back to our steps and think about it, is to make energy bar charts. So I want to represent the energy in these states here. And we'll almost always start with like kind of an initial state that I know the most about, and then I'll do a final state that's really where I have my question. So I'm going to start with one at this very first point here, and I'm going to draw that at that state, the only thing I have is gravitational potential energy, and I have no kinetic energy. So there's a bar chart to represent the energy there. And then down here at this lower state, that's where, maybe I'll draw this one in kind of green so you can see that. It's going to be moving really fast and essentially have no gravitational potential energy. So the bar chart here will look like this: no gravitational, and all of that gravitational potential energy has become kinetic energy. Now if I represent those mathematically, it's pretty straightforward. For this question here, all I have is gravitational potential energy, and the formula for that is mass times gravity times height. Down here, all I have is kinetic, and the formula for that is 1/2 mass times velocity squared. And so those are my expressions that I'm coming with there in step 2. So those are my mathematical expressions. And the next thing I want to do is just go ahead and set those equal to each other because they represent equal amounts of energy. So I'm saying these two mathematical statements must be equal. So mass times gravity times height at the initial must be equal to 1/2 mass times velocity squared. And now this is the statement that I need to be able to solve for that final velocity. So I'm just going to go through the process of solving that. So the first thing we should notice, and this is all algebra from here, there's no real physics here, just algebra. First thing I should notice is that I've got a mass on both sides, so those will cancel out, giving me that GH is equal to 1/2 V squared. And then from here, just solving with basic algebra. So I'm going to multiply both sides by 2 to cancel out the 1/2, and that's going to give me that V squared is equal to 2GH. And then last, I'm going to take the square root of both sides and get that v is equal to the square root of 2gh. Last then is just to plug in my numbers. So 2 times 9.8 times 3.5, and I'm taking the square root of that. So using my calculator off to the side here real quick, 2 times 9.8 times 3.5, we're going to get a velocity of 8.28 meters per second. So there's the final velocity of that ball. Now, one thing I want to point out here that happened is that we started with a mass in each of these, right? There's a mass there and there's a mass there. And it ended up canceling out immediately. So this is something you'll see often with energy. So if you see a question that doesn't give you what seems like a critical piece of information, sometimes you just need to start working it algebraically and see what falls out of it. So in this case, if I start working it, it turns out that the mass actually doesn't matter. So it falls out and there's nothing to worry about there. So I've got one more example here. This one, I've got a ball that's falling, and it's going to fall onto a spring. So a 1.2 kilogram ball falls from a height of 2.2 meters onto a 95 Newton per meter spring, and I want to know how far it's going to compress that spring. So starting with a doodle, there's a ball, and it's going to land on some sort of spring down here. And so there's my initial state. Maybe we'll go ahead and do the final state in green. So there's the ball compressing the spring. And again, I will do energy bar charts so that up here, I should see that in this problem, I'm going to see gravitational potential energy at the top, and I'll see spring at the bottom later. And so here I have only gravitational. Down here, I'm going to see only spring. And so if I express those mathematically, this one is going to be once again mgh, and down here it's going to be 1/2 kx squared, representing spring potential energy here and gravitational potential energy here. And once again, I'm going to go ahead and set those equal to each other because they represent equal amounts of energy, so that I get mass times gravity times height is equal to 1/2 kx squared. And then now, just to check, I'm looking for how far it compresses the spring. So I'm looking for the variable x. So I'm going to set out to solve. And again, at this point, this is just algebra. So I'm going to try and remove the 1/2 by multiplying by 2 and remove the k by dividing by k. So I'm going to multiply both sides by the fraction 2 over k. And that's going to give me that x squared is equal to 2 mgh over k. And then I'm going to take the square root of both sides and get that x is equal to 2 mgh over k. Substitute numbers. So 2 times the mass, which was 1.2 kilograms, times gravity, which is always 9.8, and then times the height, which was 2.2 meters, and then dividing that all by the spring constant, which was this 95 newtons per meter. Square root. And then again, off to the side, I'll use my calculator here. Two times 1.2 times 9.8 times 2.2 divided by 95. Let me double check my numbers. Yep. And we're going to get that it's compressed a distance of 0.74 meters. And maybe we'd rather say that's 74 centimeters. So there's the answer to that one. So in each of these, the process, I think, is pretty straightforward. We're just kind of putting the pieces together of what we've already done before, which is we're doing energy bar charts, and then we're expressing those energy bar charts mathematically. And then the idea is that these have the same, they represent the same amount of energy. So when I say the same, mathematically that's equals. So I'm going to set them equal to each other. And then I've got a useful equation that I can solve for what I'm looking for. So then you just go through the process and you're done.